What's up, fellow scholars? It's me again, Drew. I'm here to do my week 2 Excel report. Okay, let me share my screen with you. There you go. All right, now you're looking at it. With the first one, we have the speed in which we move, and I've labeled it right here if you can see. I'll add it up a little bit. All right, the speed in which we move. What I found interesting was the fact that we have some names, some weird names for things in our galaxy, like the Gomez hamburger. As you can see, let me move this out the way real fast. Move this out the way. I like the Gomez hamburger. It's just right here. It actually looks like a hamburger. Like if you have the patty right here and the two buns, and you just need some cheese and you'll be good. Also, they have Cat's Eye Nebula. Looks like exactly like an eye. And if you can't really see it behind this, but this one's called Hourglass Nebula, and it almost looks like an actual hourglass. So I thought it was pretty cool that they actually named stuff the way they look like. The speed in which we would be moving if we were on the equator would be about 1,037 miles per hour. And imagine if we had a car that would go that fast, we would never really have to be waiting on traffic. Measurement can be relative to one thing or many because it helps to determine how fast or how slow or how close or how far something is. Let's take a look. So this is around what we would actually be like if we were just standing still on the equator, and it has to do with the Earth's rotation. We also have the Earth's speed. We also have the solar system speed, the Andromeda speed, the Milky Way speed, local group speed, and this would be the whole total of all of those. And then we have our percentages and the speed in miles per hour. So if you actually take the Earth's rotation versus the whole thing, you see that it's only like really a small percentage of the whole thing. So what we are actually traveling if we are walking is just a small speed. We use scientific notation to help us express numbers that are too big or too small to be conveniently written in a decimal form. So the speed at which we were traveling through versus the whole total overall, we would have to use the scientific notation in order to describe the way that we are transformed or the speed that we are going. One helpful trick that I learned on this scenario is the Control-C, Control-V. A lot of times, or I've ran into problems before where I haven't been able to right-click and copy and paste. So I have learned now that you could just use Control-C and Control-V. That helps you do the same thing that you're trying to do. On to number 2. If some of these graphs were misleading, as you can tell from here, this is what they give us, but this is what it actually looks like. So and why people would do that for some reasons would be sometimes they may do it on accident. They just put it out there and not really check their sources and things like that, or never check what they at. They may use it to look good. Like big companies, they use a smaller percentages that will make them look really good, or bigger percentages depending on what they're trying to go for. Like here, they were trying to show that Bush has a smaller amount of unemployment rate, but if you look, they don't actually start at 0.00. They'll start at 5.1750%. But if you put it at 0, you can tell that it's not actually the way it's supposed to be. There's not even that much of a difference. So in here, they're really just trying to make Bush look good. Most of the graphs we look at start at 0.00, which is here and here. So when we look at a graph, we just assume that that's why it starts. That's where it starts at. Also, if it doesn't start at 0.00, it's not showing the whole graph. So like this one, it doesn't start at 0.00, so it looks like there's a big difference. But if we were to just look at it and be like, oh yeah, so here's a good graph, and then we copy and paste it to our reports, and then come to find out when we do put it at 0, it's not that big of a difference. And so now we just look bad because we copied and pasted. When I measured the Cartera, I can never say that word, Cartera graph, I used a shape and got as close as I could to it. And then it used another circle, and then used another circle to find out the real measurement. I found out that it's actually 13.7% rather than 4.5%. So if I come over here, as you can see, here's a Cartera, whatever it's called. They say that it's 4.5%, but I put my circle is about as big as that, and so is this. And this is actually 13.7% of the overall circle when they say it's actually 4.5. So they're obviously going to be lying to us. And that's where I say it falls in between. All right, companies look better if they say it's only 4.5 when actuality is 13.7. They may use it to look good, or like big companies may use smaller percentages than what they really have, or even a bigger percentage. It will be more consequences by making sure the graph starts at 0, 0. I will be more conscious by making sure my graph starts at 0, 0. And if it's too good to be true, then it may just be too good to be true. Okay, on to the third one. Now, the third one is about the diabetes and stuff like that. So there are 3.1 million that are obese and 23.3 million with high blood pressure and 0.03 with type 2 diabetes. You can sort the numbers by categories: obese, high blood pressure, and type 2 diabetes. Being obese without having type 2 diabetes is lower than being obese and having high blood pressure, with the odds of having all three is slightly lower at 8.5. So if you take a look here, so this is what it looks like, how many people actually have it, and then this is what it looks like. This is the percentages in between them. So if you're at 3.1% to be obese, you're at 0.1% to have type 2 diabetes, and you're at 7.2% to have high blood pressure. Now, to have type 2 diabetes and high blood pressure, you're at 0.9%. To have high blood pressure and be obese, you're at 16.1%. To be obese and have type 2 diabetes, it's only 0.9%. And to have all three of them, you're at 8.5%. And there's 3.1 million people who have both obese and type 2 diabetes. There's 3.1 million people that have type 2 diabetes and high blood pressure. So the same amount for both of these. There's 52.5 million people to be obese and have high blood pressure. And to have all three, there's 27.7 million people. I got this all from this little graph right here, and we had to go and put all these in. And according to the map, my state is much lower in obese and high blood pressure than most states. It is likely to have high blood pressure before getting diabetes. You're more likely to have high blood pressure in Arkansas more than diabetes. I found this chart intriguing. The 3.3 million people who are obese sounds unreal. However, we are a country where fast food is a hit. This processed food causes America to be obese. Okay, on to number 4. All right, this is the Army recruits and the mall shopping ones. The Army recruits are closer in height than in random mall shoppers, and the reason for this is because the random mall shoppers coefficient is greater than the Army recruits, and mall shoppers standard deviation is greater than Army recruits. Mall Shoppers has a wider box than the Army recruits, showing that they have uh, a, a greater coefficient. And the Mall Shopper heights are random, so if you get random data, but the Army recruits may be more closer to the heights restrictions. So as you can look right here, the random Mall Shoppers kind of go all over the place, whereas these are more pretty straightforward. And that's probably because the Army has a lot of rules. So if you're not meeting the height requirements, you're probably not going to be an Army recruit. Whereas a random Mall Shopper is more public, so you can have heights from 5 feet to 6 feet to 7 feet, maybe even 8 feet. Who knows? But yeah, that's probably much why they're closer together. Maybe due to height restrictions and stuff like that. And that's why this is a whole lot bigger, because this is at random. There's no height restrictions. It's just we picked these people, and one may have been really short, one may be really tall, whereas these are pretty much straightforward. Okay, now on to the sleep patterns of the Duke University students on number 5. Also, it has the household incomes as well. Here's my table. This is the mean and this is the standard. This will be around your mean, and these will be your standard deviations. The changes in the curve are just like the one with the Mall Shoppers, where the data is picked at random. The probability of you falling in between the standard deviation is about 34.1%, which would be right about here. I get about 4 to 5 hours of sleep, so my Z-score is, oh, by the way, if you all don't know, these are your Z-scores right here. And I get around 4 to 5 hours of sleep, so that would be put me like right here. So I get more 4 than I do 5, so I'll be about -1. So I'll fall into the 14% of the 217 students in this graph. The average of America income is about $50,000 a year. And the average American income is about $50,000 a year. One thing that I learned with this scenario is how to make a curve. I had never made one before. Also, I learned to make sure that the data is right, because I have messed up a lot. I'll show you one thing. I did 15 of these rather than going down to this 15, as you can see right here. So yeah, I messed up. And this is your family incomes. All right, let's go down to 6. All right. So the first entry is initial investment. If we were not to sell anything, we could be down $12,000, which really isn't good for business. As you can see here, it'll start at $12,000 because that's our initial investment. That's how much we put in to the flamethrowers, and then it goes down till we start hitting about. We can look on our graph. When we start getting closer to 200, and 200 will be our break-even point, which is right here. That's when we'll start actually making money, because that's when we have made enough to get back that 12,000. And now, from once we make that 12,000, then we can actually build up from that, and that's when we start getting our profits in. The bottom dollar is at 0. That is where you can find how much you have invested on here. It is invested $12,000. The break-even point is where your money, but not enough money to make a profit. On this graph, it's at 200. Elon has had to sell 260 flamethrowers to hit $90,000. When you start out, it may drop because people may not want the product at first, but when but then it start maybe rising up when people start talking about it, how good the product is and stuff. So like right around here, people will be like, oh, it's a new product. Da, 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 da. I'll try it. The other ones will be like, no, I won't. So you'll products and stuff will start going down yearly, maybe not profit wise, but yearly at least. And then once people are like, oh man, this flamethrower is really good. If you need a flamethrower, go to this because it's a really great one. Then that's when it usually starts picking back up, as you see, and then you'll hit that break even point, and then you can keep going from here to here is how much you really would have made money on. So that money that goes back to you is from here to here. The money that goes back to the company is from about here to here. And that is it. Thank you for watching.